Math 265A, Cuesta College. I'm Joe Vasta. We're going to cover 4.3, what derivatives tell us. We can also call this derivatives and graphs. And so we're going to actually do some definitions as we do this first problem. You can look in your book and see some of the definitions and theorems if you want to study those a little more intensely. I'm going to show you what we need to know to do our homework and to pretty much understand this. So increasing. Where is this function? So we have a function that looks like this. It's defined for all real numbers. And it asks, where is f increasing? Now f, what the whole definition of increasing, you can go look at the technical definition of increasing. I'm not going to go over that. But it's when you read the function from left to right and the function is going up. That's increasing. And when the function is going down, it's decreasing. So when they say, where is f increasing, we are going to actually answer this in terms of the x values. It's increasing all the way from down there, all the way, it's going up all the way to x equals 3. So what your book is going to write for these problems is they're going to go negative infinity to negative 3. So those are the x. Think of those guys as being on the x-axis. And all those x values correspond to points on that graph where it's increasing. And so there is the answer. Now, quite technically, increasing really should be this. It should be negative infinity all the way up to 3, including 3. But with calculus, and they do this in many calculus books, they ask for the open interval where functions are increasing and decreasing. Let's go ahead and talk about where is f decreasing. Well, f is decreasing. It's going down from this top point all the way for all x values beyond. So it's going from 3, x equals 3, all the way to infinity. So it's decreasing from 3 to infinity. Okay, now here's a new word, concave up. New words here. So where is this graph concave up? What does concave up mean? There's lots of ways to describe this, and maybe one of the ways is concave up means f lies above its tangent lines. Okay, so if I have a tangent line that is right there at that point, f is lying above it, and f is lying above it. But then once I get like right here, maybe at 3, 5, then f is lying below it. Another way of thinking about concave up is the curvature is actually curving up toward the sky. So look, it looks like it's concave up, and it sort of looks like the curvature is facing the sky. Another thing that I've heard, I've seen this in a book to remember for concave up. They have this phrase that says, concave up, pass the cup. Okay, so whatever, because it looks like a cup. So concave up looks like all this, the curvature is toward the sky, or the tangent line's below each point on that one, and then it starts being the curvatures like sort of facing the ground right at this point here, and we'll just approximate it at this point. So it's going to be concave up for the x values from negative infinity up to this point right here. And so for concave up, we'll say negative infinity to the x value 2. Now, concave down one way of looking at that is f lies below its tangent lines. But maybe the better way is the curvature is facing down. Or here's another clever thing that someone came up with. Concave down. Why the frown? Yeah, because a frown is concave down. How clever is that? So that kind of looks like a frowny face right there. So the curvature is facing the bottom from the x value of 2 and all the way on. Okay, at least from what we can see. So from x equals 2 to infinity, your graph is sort of frowning. It is concave down. And so those are the definitions of increasing, decreasing, concave up, concave down. You can look in the book and see some more technical definitions of increasing, decreasing. But there's a lot of stuff in this section, so I wanted to make sure that I hit some examples and not get too caught up on the technical definitions. If you're a math major or a technical person, you can look at these definitions of increasing and decreasing and see also why that maybe with increasing, decreasing, we should have the closed interval. Now here's something that we have here is local maximum, or local maxima. Remember we said that, so I'll just say local maxes. Those are tops of hills, and they have to be interior points. And we do have local max at 3, 5. And it looks like an absolute max as well, but they didn't ask for that. Local mins, so these two are kind of a review from earlier in this chapter. Local mins, do we see any bottoms of valleys? No, we don't. So our local mins will be none. Now here's a new word, inflection points, and these are the points. I'll just say the point is an inflection point is the point where the graph changes concavity, where the graph changes concavity. Now, what do we mean by changes concavity? We mean that it goes from concave up to concave down, or vice versa, it goes from concave down to concave up. Well, this point right here was the point where it went from the curvature facing up, concave up, to the curvature facing down, concave down. So the inflection point happens to be 2, 4. Now be careful, because your book, when they say, hey, find the local maximum, they might say the local maximum value, which is 5, or they might just tell you the location when they say find the local maximum value, and they'll say x equals 3 or something. So know that the local maximum really is a point. The first number is the location, which is important, and the second number or coordinate is the value. The local max value is 5, the local max location is 3. So we've just covered in this simple example basically a lot of definitions in 4.3. So if you want a different perspective, you could actually read the book on 4.3 and see how they approach some of these things. They kind of baby step it, but I just say let's just take this all at once, because I think it's good to do that. Let's go ahead and look at our next slide here, and hopefully this thing right here isn't too blurry, or the font isn't too small. Let me just stand up and see. If not, you can go look at the PDF on the website. So look what I have here. I have two functions. I'll call this function 1 and function 2. And this function, it kind of looks like a parabola. And I have some points here, like at this point, the slope, that's f prime, is -2. And at this point, the slope is -1, -1/2, 0, 1/2, 1, 2. So f prime, that's the first derivative, is positive when, just looking at this top graph, when f is increasing. And notice, like, look right here. You have f prime is 2, f prime is 1, f prime is 1/2. I mean, maybe f prime here is 0.001, but that's when this graph is what? It's when it's increasing. F prime is negative, like on those values there, or on those values on function 2. It's negative when f is decreasing or going down. Okay, so that's what we really want to drive that point, that this is f prime is positive, the function is going up. F prime is negative, the function is going down. That will always be the case. You can draw other functions and investigate that, and it will always be true. Here's the one that's a little tougher to see, but we'll see if we can see this. F double prime is positive. Okay, so f double prime is the second derivative. It is the rate of change of the slope. So the rate of change of the slope, that means how is this slope changing? Look, it's going -2, -1, -1/2, 0, 1/2, 1, 2. So this top function, the rate of change of the slope is positive because it's increasing. Do you see how the slope is increasing as I move along this function? So when the rate of the change of the slope, which is f double prime, is positive, which we have up here, then f is concave up. And you could probably guess what's going to happen here. When the rate of the change of the slope is negative, look what's happening here. You're going 2, 1, 1/2, 0. It's decreasing the rate of the change of that. What's happening, it's changing, it's becoming more negative. So f double prime is negative. That's going to tell you that f is concave down. Why the frown? And then that f double prime was positive. That was concave up, past the cup. So that is very, very important. The second derivative tells us the concavity. If it's positive, concave up. If it's negative, concave down. I think now we're ready to do a problem that covers a lot of problems in your homework. So let's go ahead and do this problem. We have a function, it's a polynomial. They ask us to find the intervals on which f is increasing and decreasing, find the local maximums and minimums, and really I should say maxima and local minima, oh well. Find the interval on which f is concave up and concave down, find the inflection points, graph the function. Now this graph the function is something that is really covered in the next section, but I figure we might as well cover it here. Might as well see some of those right now. So this is what we're going to do. We're going to first take the derivative of that. We're going to take the first derivative. And the first derivative of our function happens to be 4x cubed plus 12x squared. 15 is a constant, so we don't care about that. So the next thing I'm going to do after I take the derivative is set that derivative equal to 0. So 4x cubed plus 12x squared, set it equal to 0. And what am I finding when I do that? I'm finding the critical numbers. So I factor out maybe a 4x squared, and I have an x plus 3. This equals 0. And I set each of these things equal to 0, and I get two numbers, 0 and a -3. And these are known as critical numbers. And I think your book calls them critical points, but these are critical numbers. And so I have these critical numbers. I'm trying to find the intervals on which f is increasing and decreasing. So what I'm going to do now is I'm going to put a number line. And on my number line, I'm going to put -3. Then I'm going to put 0. So I'm going to put those in order. And I'm going to do something called the first derivative test to find the local mins and maxes. But before I do that, I'm going to find the answer to part A, where it says find the intervals of increase and decrease. So how do I do that? What I'm going to do is I have 3 intervals to check. And I'm going to check to see if they're positive or negative. And so my first interval to check would be, I'll do it over here, -infinity to -3. And then I'm going to check from -3 to 0. And then I'm going to check from 0 to infinity. How am I going to check this? I'm going to go ahead and, this right here is my function. I'm going to go ahead and put a number in this interval into this derivative. And so like a number that's in here would probably be like maybe -4. So we'll put -4 in there. So what I'm really doing is I'm going f prime of -4. And what I'm looking at is just the sign. So -4 there, that's going to be 4 times -4 squared, that's positive. And -4 in there is going to be a negative. So the sign on this is going to be negative. So any number that I put in here will be negative. Those are negative signs. Now let's go ahead and put a number in this interval in, maybe -1. And I look at the signs here, and you could either put it here or you can put it up here. When I put -1 in, I get 4 times -1 squared, that's positive. And I put -1 there, that is positive, which gives me a positive. So we have pluses right here. I could have put in -2 or -2.5, I would have got the same results. Now I'm going to pick a number in the third region, maybe 5, and I'm going to put that into the derivative. So I have positive and positive, which gives me a positive. And so we know that this right here is also positive. So what does this describe? This describes where f is increasing and decreasing. So let's go ahead and talk about that. Increasing means going up. And this is going up when you have pluses. So your graph starts going up where at? -3. From -3 where? All the way to infinity. That's when we're increasing. Where is this graph? This is the derivative. So let me go ahead and put f prime right next to that number line. Where is this derivative decreasing? Where it's at negative, it's negative from -infinity to -3. And we say there it is decreasing. And so that answers part A. Now part B, this is called the first derivative test. And the first derivative test, I think I'm running out of paper here. So I'm finding the local mins and maxes. So we'll go like this. I know we could hardly see the question anymore. And let's go ahead and do this. This graph is decreasing. It's going down. So it goes down there. And then what happens here? It goes up. Now when that happens, when it goes down, when it goes from minus to plus, that means that we have just found a local min, because it's going down and then it goes up. Now this is going up and going up. So what is this guy? This guy is not a local min or a max. And so that is what the first derivative test does. The first derivative test tells you you can look at this sign chart here of the first derivative and find the local mins and maxes by when the signs change. And so I have a local max. Well, I don't. So that's none. And local min, and we're going to say our local min as at -3, that's the x value. How do I get the y value of the local min? Let's bring this like this. I go ahead and I stick -3 into the original function. So that's -3 to the 4th, which is 81 minus, would that be, I don't know. So you end up getting some number. We can put that in our calculator, and what I got when I calculated this was -12 for the y value. So that is the local min. It is -3, -12. That answers part B. Find your local extrema. Okay, the next question asks, find the intervals on which f is concave up and concave down. Okay, so to find concavity, so to find increasing, decreasing, it's the first derivative. To find concavity, it is the second derivative. And the second derivative, let's find our first derivative, it's right there. This is going to be 12x squared, and then we have plus 24x. Now to find the concavity, we set the second derivative equal to 0. That's kind of what we did with the first derivative to find the critical numbers. So what am I finding here? Well, we'll find out pretty soon. Actually, there's an x there. Almost forgot it. I'm going to factor out a 12x, and I'm going to have x plus 2. This equals 0. And my points will be 0 and -2. Now, I can't call these critical numbers. They are the critical numbers of the first derivative, but what I'm going to call them is IP candidates. Now, IP candidates, what does that stand for? That's inflection point candidates, and that's what those are. So over here you had critical numbers, and the critical numbers are just candidates for mins and maxes. The inflection point candidates are candidates to be inflection points. And look at, this was like a little election here, and on -3, he was voted local min. There could be more than one local min. And 0 lost the election. That's sad. So he just went home. Well, the same thing's going to happen here. We have some candidates for inflection points, and we'll see maybe they'll both win the election and they'll be inflection points. So what am I going to do with those? I'm going to go ahead and put these guys on a number line, and now this number line will represent the second derivative. And so what we have here is we have -2, and then we have 0. And I do the same thing that I did over here when I found the pluses and minuses, except now I'm putting things into the second derivative. So let's go ahead and do that. I have 3 intervals to check. My intervals are -infinity to -2, -2 to 0, and 0 to infinity. So let's pick some values here. So I'm going to go ahead into the second derivative. I'm going to plug maybe -3. And here's the second derivative right here, if you'd like. So this is going to be 12 times negative 3. That's a negative. And then this is, this equals negative. Negative 3 in there is going to also be negative. Two negatives make a positive. So all these guys right here have pluses, which actually mean, it doesn't mean it's increasing, it means all those guys on the original graph are concave up. Let's go ahead and put a number inside this from this interval, maybe negative 1. And we're plugging it into the second derivative. And I'll plug it into this one right here. So this is a negative 12, so this is a negative times a positive, which gives me a negative. So all these guys are negatives. So it looks like what happened is we changed from pluses to minuses, which means this guy, he is an inflection point. So he kind of wins the election. Let's go see if the other guy does. So we'll do a point from 0 to infinity. I'll go ahead and pick 20. Doesn't matter, as long as I pick something in that interval, I get a positive and a positive, which give me a positive. So looks like the signs changed again, and this guy's a winner as well. He's an inflection point. And we are answering question C, which says find the intervals on F. Find the intervals on which F is concave up and concave down. So here's concave up would be everywhere there's the pluses. So I'm going to write everything in terms of open intervals, negative infinity to negative 2, and then we're just listing them out here, and then we have 0 to infinity. And concave down would be where we see the negatives. So this is negative 2 to 0. And so that answers part C. Part D is almost immediate from this. Part D asks for the inflection points. And the IPs, or the inflection points, there's two of them. They are negative 2, comma, something, and 0, comma, something. Where am I going to get those y values? The answer to that is we're going to get those y values from this original function. So you'll put a negative 2 in there, and that's going to give you 16. This is going to be minus 32 plus 15. It's a negative 1 there. And then you put 0 in there, you end up getting a 15. So those are your inflection points. Now, what are we doing? Is this 4.3? 4.3 is not going to ask you to graph them. That will be the next section. But we're going to graph this nevertheless because we want to get ready for the next section. So let's go ahead and make a graph of this. And so we're going to be sure to draw the local mins and the maxes and all that stuff. Let's go ahead and do the graphs. So look what I have here. I have inflection points and, oh boy. I'm going to go ahead and write out, sometimes it's easier to use the whiteboard. I'm going to say, we had a local min at negative 3, negative 12. Okay, so that way we have that information. What I'm going to do is I'm going to fold this piece of paper. Oh good, we have the concave up, and I'm going to put it right there. And I'm going to, I see that negative 3's here and negative 2's there. Okay. I'm going to go ahead and draw another number line that captures some of the information here. Okay, so let's go ahead and do that. So here is a number line. And I'm going to put some key points on here. I'm going to put negative 3, negative 2, and 0. So I'm going to put all my important things here. critical numbers, IP candidates, and let's see what happens. So the part where it's decreasing, I'm going to use a red pen. So this is the part where it's decreasing, and I'm just going to make this, I'm going to just draw red right there. And the part that's increasing, I'm going to use a blue pen, or a blue highlighter, I guess. So this is just going to kind of help me draw the graph. And then I'm going to look at what happens to the concavity. So this says it's going down and it's concave up. So going down and concave up means this. Now between -3 and -2, it's still concave up, but now it's going up. So concave up going up looks like that. Now the rest of the graph is going to go up, so everything that I do will go up on these ones. This is going up and it's concave down. Now going up concave down looks like this. So that tells me concave down, and then I'm going up because I can see the pluses. And then the last one is going up, concave up, which looks like that. Okay. I think we can draw this graph now. I hope we can draw the graph. I'm going to just use another piece of paper. And I have, there's the y-axis, the x-axis. The scaling might be a little funky here. I have inflection points of 0, 15. I guess I'll just put that right there. And -2, -1, -2, -1. And let me see what else I have. -3, -12. So -3, -12 is right here. So I'm not putting tick marks here. And -2, -1 right there. And so let's see if we can draw this graph. Oh, and I actually didn't line it up with that, but that's all right. So this right here is -3. This right here is -2. Here's 0. So those are the important things to look at: -3, -2, and 0. And so to the left of -3, it's going to be decreasing in concave up. So it's going to look like a parabola. So it's going to kind of look like this. That's what this information tells me. And I know it's not lined up exactly with that, and maybe I should have. Now between -3 and -2, it's going to be concave up going up. Now the rest of this graph is going to go up. So between -2 and 0, I'm still going to keep going up, but I'm going to go concave down. And so when I go concave down, and then when I hit 0, I'm going to still go up, but now I'm going to change it back to the cup, concave up past the cup, and it's going to go like this. This right here is the y-intercept of 15. We have -3, -12. This is the inflection point, -2, -1. And then, of course we can call this point 0, 15 if you want. That is a rough graph of f using the, I know we have, we have the other number lines, we use both of those number lines, but this was the rough graph of f using the first and second derivatives. So hopefully that helps us. Now that was quite a problem for problem number 1. But there's one more thing that I'm going to ask us to do, and because they ask you to do this in your homework. This is sort of a review from an earlier section. I think it was 4.1. Find the absolute extrema on the closed interval -4 to 1. So to find the absolute extrema, remember what you do. You put -4 and 1 on the list, and then you put any critical numbers that fall in between there. Now you had critical numbers of 0. So here's some critical numbers here. You have critical numbers of 0 and -3, but nothing ever panned out with 0. I mean, you can still put him on the list if you want. You can still put -3. You really don't have to put 0 on because 0 was not a min or a max, but we'll still put him on there. And then you just go f of each of these values. And when I say f of each of these values, we're plugging them back into the original function. And with the original function, that's the x to the 4th plus 4x cubed plus 15. So f of -4, I end up getting 15. The f that I'm plugging this into is that guy right there. Okay, f of -3, -12. F of 0, which we really don't need to do, that is 15. And f of 1 happens to be 20. So which one is the top dog here? The top dog is that guy. And which has the lowest value? This one is the low. So when they say find the absolute extrema on there, on this interval right here, the absolute max happens to be 120, and the absolute min happens to be -3, -12. Now that is only restricting the domain there. So if you didn't restrict the domain, there would not be an absolute maximum. There's an airplane going over. Let's go ahead and pick up all of these pieces of paper here. So let's go ahead and look at some other things now. Finding local mins and maxes, and if you look really close, there's some white out on this page because I messed up, but I didn't want to rewrite it all again. Finding local mins and maxes. We have the first derivative test. So when we put our critical points, no, that's the wrong one. When we put our critical point numbers on the number line and checked pluses and minuses and did that, we were doing something called the first derivative test. Okay, so the first derivative test, that's what we were doing. Critical points, suppose it had A, B, and C, you'd put them on the number line, and you'd find that A is what? A min or a max? Let's see, it goes up, so this is just a general thing. It goes up and then goes down, so A is a local max. B, well, he doesn't change from minus to plus or plus to minus. He's sort of an imposter. He's trying to get in to becoming an extrema, but he's just an imposter. And C goes down and then up, which makes him a local min. So the first derivative test is a way of finding local mins and maxes. But there's something that is in all calculus classes called the second derivative test, which is the test to find what? Local mins and maxes. So here's the second derivative test. You've got a critical point C. I'll just pick one. Suppose the second derivative is continuous on an open interval containing C and that f prime C is 0. So it has to be a critical point that is gotten by zeroing out the derivative, not making the derivative undefined. It says if the second derivative is greater than 0, which really means it's concave up, doesn't it? Then C is a local min. If the second derivative is less than 0, which means, this is negative, it's concave down, then that thing happens to be a max. If the second derivative at that point equals 0 or does not exist, then the test is inconclusive. So the first derivative test is actually more powerful. Why do I say that? Because it always works. It's more powerful than the second derivative test. So why would we do the second derivative test? Well, just so you know what it is, because this pops up in higher dimensions in a Calculus 3 class. In higher dimensions, you don't even have a first derivative test anymore, and you're just left with the second derivative test. So we assign a few problems that have the second derivative. If you went back and did the second derivative test, I've got to find out where all my stuff is here. Where is it? So let me go ahead in a different color. So on the homework, I'll assign a few where they ask you to do the second derivative test. So the second derivative test says you take these critical numbers. I think so. This is problem number 1, second derivative test. And you actually need the second derivative. The second derivative happened to be 12x squared plus 24x. And you would put each of these critical numbers in. So we have critical numbers 0 and -3, and you'd put them into the second derivative. So if you put 0 into the second derivative, you end up getting 0, which means inconclusive. How great is that? So if that happened, you would have to then go and do the first derivative test, do exactly what we did over here. The second derivative evaluated at -3. I went ahead and did that. Well, that's 9 times 12, but you'll end up getting a 36, which means, so this tells you that's positive, which means x equals -3 is a minimum. Okay? So the second derivative test, it's great, you should know what it is, but the thing that's always going to work, the more powerful thing, is going to be the thing that we did with that example, which is putting the pluses and minuses on the number line. Let's go ahead and do another problem. I'm going to check how blurry things are. Okay, so looks all right to me. I'm going to go ahead and find all the things that they asked us to find in the other problem. I'm not going to do the closed interval thing. I'm trying to find the other problem. You know, increasing, decreasing, local mins and maxes, concavity, and inflection points, and then I'll try to do a rough sketch of that graph. So the first thing that I want to do, I will take the first derivative and see what I end up getting. The first derivative is the power rule, so it's going to be 3 times 2/3 x to the 2/3 minus 1, so this is -1/3. This is going to be -1. So this is going to give me 2 over x to the 1/3 minus 1. And what am I going to do? I'm going to get a common denominator of x to the 1/3, x to the 1/3. So on the top I have 2 minus x to the 1/3. On the bottom I have x to the 1/3. And that is the reason I put it into one fraction, is I'm going to find the critical numbers. To find the critical numbers, so the critical numbers, I set the top equal to 0, and I set the bottom equal to 0. Now notice that this function, its domain is all real numbers, because I'm taking a cube root, and you can take the cube root of negative numbers. So I'll do this one first. X is 0. How did I get that? I cubed both sides, and 0 cubed is 0. So on this one, I'm going to add x to the 1/3 to both sides. So I have x to the 1/3 equals 2. I'm going to cube both sides, and I end up getting x equals 8. So my critical numbers, I know I wrote that 2 times, would be 0 and 8. I'm going to go ahead and put those critical numbers on a number line, 0, 8, and I have 3 regions to check. My 3 regions would be from negative infinity to 0, 0 to 8, and 8 to infinity. This represents the first derivative. This represents when things are going up and down. So if I pick something over here like negative 1, f prime of negative 1, let's see. I've got to put this into the derivative. If you like, you can write the derivative as 2 minus the cube root of x all over the cube root of x. You can use this one, 2 over the cube root of x minus 1, but in any case, if I put negative 1 in there, I'm going to end up getting cube root of negative 1 is negative 1, 2 minus a negative 1, so I get a positive on the top and a negative on the bottom, which gives me a negative. So all these guys right here are negative. I'm now going to put 1 into the derivative, and I have 2 minus 1 on the top, that's positive, and 1 on the bottom. Positive over positive is a positive, which means we have that right there. I'm going to go ahead and put 10 into the derivative, and if I put 10 in there, I'm going to end up getting, maybe I should have put 27 in there, but I'm going to end up getting a negative on the top and a positive on the bottom, which gives me a negative. Okay, so there was an election. These guys were in the election. They wanted to be local extrema, and they both won. So we could actually answer increasing, decreasing, local max, local min, all with this diagram. And that's why I like the first derivative test to find local mins and maxes better than the second derivative test to find local mins and maxes. The second derivative test comes up in Calc 3, and when you get to that, you'll just learn it when you get to that. I mean, it's good to know it here, to do some homework, maybe a test question, but this is more reliable. So let's answer some questions. Increasing. The graph is increasing from, that means going up. So this says the graph is going down, then going up, then going down. It's going up from 0 to 8, and we'll just use open intervals. The graph is decreasing, going down from negative infinity to 0. And we're not going to put the union, we're just listing the intervals, and from 8 to infinity. So there's increasing, decreasing. Okay, local max and local min. Okay, local max, well, let's see. Let's find out what this first guy is. It goes down, so you can think of the graph goes down and then goes up. So that guy right there is a min. Local min of 0, comma. The y value would be gotten by plugging 0 in there, so it looks like it's 0, 0. Here you're going up, and then you go down. And so that looks like a local max at 8, comma. You put 8 into the original function, you have the cube root of 8, which is 2. 2 squared is 4. 4 times 3 is 12. 12 minus 8, whew, that was traumatic, is 4. I should just be using calculators all the time. And there happens to be increasing, decreasing, and local max, local min. Let's go ahead and continue this problem on another piece of paper. And hopefully when you see the second one, you feel more confident, in terms of what we're learning here. There's a lot of stuff in this section, but I think you'll be all right if you practice some homework and pay attention to the lecture here. I'm trying to find inflection points in concavity. Here was my function here, f of x equals what is it? F of x equals 3x to the 2/3 minus x. And so my first derivative, whoops, I don't know what happened there. The first derivative, there were many forms of it. It was this, and then this, and then this, and then this. So I'm actually going to write this one out. I'm going to write 2x to the negative 1/3, 2x to the negative 1/3 minus 1. Okay, so that's what I have for my first derivative. Why am I writing that? Because I need to calculate the second derivative. And I don't want to do, sure, the first derivative looks like this. I don't want to do the quotient rule there. I'd rather just do the power rule, and the derivative of negative 1 is 0. So the second derivative is going to be 2 times. I'm going to go negative 1/3. So this is the power rule, x to the, then we subtract 1, so negative 4/3. And then that's plus 0. So my second derivative happens to be, what does it happen to be? It happens to be negative 2/3 x to the negative 4/3. Or you can write it as negative 2 over 3x to the 4/3. What am I going to be doing with that second derivative? I'm going to be finding the so-called critical points, but we call them, what did we call them before? The IP candidates, the inflection point candidates. How am I going to get those candidates? I'm going to set the top equal to 0. Well, no, we're not going to do that. And then we're going to set the bottom equal to 0, in which you end up getting 0. So your inflection point candidate, there's only one. That'd be funny if you lost this election, but I mean, and it's just 0. So IP candidate is 0. I'm going to go ahead and put that guy on a number line, and I'm going to check 2 regions. My 2 regions to check would be from negative infinity to 0, and from 0 to positive infinity. This is the second derivative, and I'm going to be putting test points into the second derivative, which would be one of those. So maybe I'm going to go with negative 1 on this one. So if I put negative 1 into here, I take the cube root of negative 1, which is negative 1, and then I take it to the 4th power, which is positive. So I'll have negative on the top and positive on the bottom, which gives me a negative power, a negative number. I'm going to go ahead and maybe put 1 into the second derivative, and I have a negative on the top and a positive on the bottom, which gives me a negative. So it looks like the whole number line gets negatives. And so, let me go ahead and bang on the window. There's some noise outside, so I'm going to now get back to this. And so we have, what does this tell us? Is 0 going to be an inflection point? And the answer is no. The concavity does not change going from this part to this part. So we have concave up. Do we see any pluses? Well, concave up, there's none. Concave down would go from negative infinity to 0, and from 0 to infinity. Okay, so we don't include the 0 because it's still some sort of IP candidate. We'll see what happens when we draw the graph there. So now what we have is inflection points. For inflection points, we are going to put none. And that ends the search for inflection points in concavity. What we're going to do now is we're going to graph this thing. So I'm going to get another piece of paper, and we are at the 54 mark. And I'm going to kind of reproduce some of the number lines that I had. Here was the first derivative, And here is the second derivative. And we have 0, 0, and 8. And so I'm just recreating what I had here. We have negatives, positives, negatives, and then over here was all negatives. Okay, so what I'm going to do is I'm going to draw a number line that goes right below, and it has 0 and 8 on there. The graph is going down. I'll put it in red like I was doing before, and the graph is going down here, and the graph is going up right here. Now what I'm going to do is I'm going to say the graph is going down and it's concave down, so that's going to look like that. The graph is going up, it's concave down, so it's going to look like that. The graph is going down and it's concave down, it's going to look like this. And let's go ahead and draw this graph now. I'll try to line things up a little better in terms of how I'm doing this. This is X. This is Y. We can take a look at this. We have local max at 8, 4. So I'm going to put a local max there. And the graph goes down. 0, 0 was a point on the graph. It wasn't an inflection point, but it's going to go down here. It happened to be a local min. So this is a local min, and this is a local max. And so when you put these two things together, you're going to end up getting a graph. There's the concave down, and then it's still going to be concave down, the rest of the way. You're going to end up getting a cusp. And then this graph is going to go like that. And this max happens to be at 8, 4. You can find the x-intercept by setting y equal to 0. You'll end up getting a 27. So there is a picture of the graph. I'm a little happier with this graph than the other one because I was able to throw, that's not up to scale, I was able to throw those numbers right below. So that ends problem number 2 for this. So problem number 3, we're given a graph of a parabola, and they're asked to find the critical numbers, increasing, decreasing, local mins and local maxes, but of f, and not of what the parabola is, which is the derivative. So if you get something like this in your homework, it seems like it's going to be a little difficult doing this problem, but what I would suggest is drawing a number line, and that number line represents f prime. Now sometimes f prime is positive, that's above the x-axis, and sometimes it's negative, that's below the x-axis. Let's go ahead and put this 3 right here, and the 7 right there, and where the slope, this represents the slope, where the slope is positive, is above the x-axis from negative infinity to 3, and it's also above the x-axis from 7 to infinity. Now where f prime is negative, it's below the x-axis. And look what we have here. We have the graph, the original graph of f is going up, then down, then up. So that's not saying about this graph, it's saying about the graph of original f, which we don't know what it is. We also see that these guys right here, 3 and 7, are the critical numbers. So when they ask us, find the critical numbers of f, then we can see that they are 3 and 7. Where is f increasing? And this is the f that we don't have. This is f prime. F is increasing. Let's just look right here at this derivative graph here. It's increasing from negative infinity to 3, and it's also increasing from 7 to infinity. It's where the pluses are. Where is f decreasing? Well, this tells me where things are going up and down on f. It's decreasing from 3 to 7. Local max of f and local min of f, we can find that those when the signs change. When you're going up and then you go down, that makes this a local, so going up and then going down is a local max. And then going down and then going up is a local min. So the local max of f is at 3, at x equals 3. I'll just say the location because it doesn't tell me what the max value is. This is just the derivative graph. The local min of f is at 7. So that completes problem number 3. Just make sure if you get one in your homework to do the sign chart of whatever graph it's describing. So here's the funny part. We're going to do another one, and the graph looks the same. It's the same parabola. But look at this. This is now the graph of some function. It's different from the last one in the terms of this guy is the second derivative. And the second derivative describes the concavity. So let's go ahead and put a number line down, and here is f double prime. I'm going to go ahead and put the 3 here and the 7 there. And the graph is concave up if the derivative is positive, and concave if the second derivative is positive, and concave down if the second derivative is negative. So this graph here of the second derivative is positive. Reminds you of the last problem, except these things are telling you different things. It's positive from negative infinity to 3 and from 7 to infinity. And it's negative between 3 and 7. Okay, that's where we have the second derivative. We get it from that graph. But now this is going to tell us not the original graph of f is going up and then going down, then going up, because this is not the first derivative, it's the second derivative, which tells you that the original graph is concave up, concave down, concave up. So with this diagram, we should be able to answer these pretty quickly. The original graph is concave up, where you see the pluses. Negative infinity to 3 and 7 to infinity. The original graph is concave down, where you see the minuses from 3 to 7. And the inflection points are where they change concavity, and we change from concave up to concave down at 3. And we change from concave down to concave up at 7. So that completes problem number 4. Why don't we go ahead and do our last problem of 4.3, which happens to be one of those problems where you try to figure out what the original graph looks like. So wow, let's see if we can do this problem. F prime is, so you're going to get something like this in your homework, and if you look at your homework list, I actually put those numbers, the ones that have things like this, near the end of the list. So you probably want to do these after you've done some of the other ones. So I'm going to go ahead and draw a number line. I'm going to call that f prime, and I'm going to draw another number line, and I'm going to call that f double prime. Hopefully I have enough room to do this. And I see some numbers 1, 3, and 5. So 1, 3, and 5. Okay. F prime is greater than 0. That means positive from negative infinity to 1. And it's going to be negative less than 0 from 1 to infinity. Okay, f double prime, which is this guy right here, is positive or greater than 0 on from 3 to 5. So I'm going to go ahead and put pluses there. It's going to be less than 0 or negative everywhere else. Okay, so those are negatives. Okay, so let's go ahead and draw another number line, and I like to do it this way. I don't know if the book does it this way. It doesn't really matter. I'm going to put a 1 there, a 3 there, and a 5 there. And I usually use red and blue. Red meaning the graph is going down. The graph is going down. The F prime tells you that. It's going down from here all the way to infinity. And the graph is going up from here to there. In each of these regions, I'm going to put the little, this is going to help me with the concavity. This is going up and it's concave down, which means it looks like that. This is going down and it's, those are negatives there. It's concave down, so it looks like that. It's going down and it's concave up, which looks like that. There's actually only 4 choices you have, and you can think about what are all those 4 choices. And then it's going down and it's concave down, so it looks like this. I'm going to have to use another piece of paper. And so let's go ahead and draw this graph, if we can draw the graph. X, Y. So, you know, maybe we could just, I mean, that's not a vertical asymptote. I'm just trying to line this up here. Here's 3. And then there's 5. Okay, so it looks like right here, it goes up and then down. I end up having a max. So this gives me a max. And then I don't have any other thing. So where do I put the max? It doesn't tell me, you know, you can't see the original problem now, but it didn't tell me where it was. So I'm just going to go ahead and put it right here. And I'm going to, whoa, there's like, this thing has stuff on it. That's going to be concave down on both sides of this. So this is going to be concave down that way and concave down. Now, look what I have to do at 3. I have to change its concavity. So that means I'm going to change it between 3 and 5 to concave up. But then at 5, and I'm always decreasing, I'm going to change it back to concave down. These points right here, this guy and this guy, these are inflection points. And then this guy right here is a local max. And the answers, you know, might look a little different depending on it. You may have decided to put your local max down here, and then your graph would have been shifted a lot lower. Oh, so you might not see the full graph there. There's the full graph. So this concludes a very long section. It seemed like we were doing a lot of stuff. We actually did some 4.4 when we do the graphs. We're doing some 4.4. So I'm going to come back and do 4.4 on the next lecture. You guys have a good week. Take care.